Hi everyone, we're Team Dimensional, and today we'll be walking you through our game, Dead or Alive, and how we used it to study human trust in AI. I'm Ishika.
I'm Rainer.
I'm Yuval.
And I'm Kishan.
We'll start off by introducing our research question, which backs up all of the steps that we took to make this game. This question asks how limited communication and changing AI accuracy affects a player's willingness to trust AI. In our game, the player cannot clearly see everything, so they must decide whether to trust the AI or rely on what they can observe. Our original hypothesis was that players would trust the AI when its accuracy was low, its communication was limited, or the player had low visibility. We expected players to choose safer, short term rewards instead of risking them for uncertain future rewards. But throughout the game making process, we discovered conflicting information. To test this, we created a decision making game called Dead or Alive. Before the game starts, players choose a driver vision level of low, medium, or high. This controls how clearly they can see the road. During the game, players see a foggy scene and must identify the target. It could be a healthy human, injured human, zombie, or medical item. For this part of our research, we wanted to test how the level of driver vision affected a player's decision. To measure this, players made the decision to skip, squish, save, collect, or scram. Every action uses a different amount of time. Players also had a limited ambulance capacity. Once it fills up, they must choose whether to return to base or keep moving forward. The AI observer provides a prediction of the current target and a preview of the next four targets. However, its accuracy may be known, unknown, or unreliable. This forces the player to decide whether to trust the AI or their own judgment. This setup allows us to observe how players make decisions when they have incomplete information and uncertain AI guidance.
Now I will talk about the AI that is used in our game as well as how they are trained. The observer is implemented using a YOLO model from Ultralytics. It takes in the raw observer view generated in Unity and labels the different items in the image with bounding boxes, as shown in the graph here. We successfully trained the model to reach a 92.3% accuracy with minimal overfitting. Additionally, we used the confidence threshold cutoffs to artificially lower the accuracy. This allowed us to simulate three different accuracy models without having to train three individual models from scratch. We also utilized a CNN image classifier that analyzes the driver's view and identifies the type of entity it sees. This works alongside a reinforcement learning model that first commits to a decision blind and then reevaluates its choice once observer feed is revealed. Finally, we include a pure human observer game mode, which is a version we provided to our human playtesters.
Now I'll talk about our data collection and experimental variables. So we structured playtesting across two main phases. First, we hosted live Zoom sessions and gave remote control access, as you can see in this demo picture. We used a game instruction script to ensure each player played with the same intentions of maximizing their score. Although we found some qualitative insights, individual runs were time-consuming combined with their script. So after our first day of playtesting, we were able to develop a web app and share it in our Discord channel, as you can see in the picture below. Next, I'll talk about how that data was actually collected in the game. To track behavior, the log turn function triggered in the background the instant a player acted, and it packs data from their move, capacity, and settings into a single row so every turn has full context. When the game ends, the system automatically saves every column into a CSV spreadsheet. Here's an example of Rob, our instructor, playing our game and what the name of his CSV file looks like. This gave us data to evaluate our key variables. So we had three main independent variables: AI observer accuracy, vision difficulty, and whether or not the accuracy was disclosed to the player. And here are some of the dependent variables we collected in connection to our original research question. So, for instance, we tracked whether or not a player changed their action after accepting an AI guidance to gauge their trust in an AI. Additionally, we tracked player actions, decision latency, task outcomes, and these are the controlled variables, or the constants.
Moving on to how AI accuracy affected player decisions. We analyzed 128 session logs containing 2,543 decisions. After removing incomplete data and sessions with fewer than 5 decisions, 91 reliable runs remained. Players changed their decisions most often about 27% of the time, when AI accuracy was between 50 and 70%. When accuracy reached 95 to 100%, decision changes dropped to about 14%, likely because players already agreed with the AI. Visibility also played an important role. As driver visibility decreased, players relied more on AI's guidance. When visibility was higher, they were more confident in their own judgment and mainly used the AI just to cross check their choices, often disregarding its classification when it conflicted with what they believed. Overall, the AI information had the most influence when players had limited information. Next.
Now I'll be talking about additional observations on player behavior. Players compared AI recommendations against high vision and were able to quickly realize when accuracy was low. Once verified as unreliable, they felt no use for the AI observer. This proves that players need enough evidence in order to trust an AI. Noticing that's not depicted in the graph, but is definitely important, is that most players forgot they could toggle the AI feed off unless explicitly reminded. Without toggling it off, players defaulted to static habits, either always accepting and keeping or always declining advice without evaluating it dynamically. Looking at the first graph on the bottom, when players first started playing on high vision, they used skip a few times. However, as the turns and rounds progressed, players abandoned skips in favor of squish to clear board space and reach future rewards faster. Moving to the graph on the bottom right, across 49 game sessions, the majority of players never picked up a zombie. We can conclude this is mostly because a zombie represents a high risk, high reward asset, and most people weren't willing to take that risk if they weren't confident in an AI observer. Hiding humanoid identity in the ambulance inventory led to forgotten zombies. Half of the players who actually loaded zombies forgot to cure before the game ended.
We also compared the data from our human playtesters directly against the gameplays of the reinforcement learning model. If you look at the graphs in the upper image, an interesting trend emerges regarding information asymmetry and trust. The AI driver frequently overconsults the observer's feed, checking it nearly 94% of the time, and is highly decisive, switching its initial decision about 70% of all those cases. Human players, on the other hand, pay far less attention to the AI observer's feed and rarely act on it. Another key finding is how each driver reacts to incorrect data. When the AI observer makes a mistake, the AI driver's performance is surprisingly resilient. However, human drivers exhibit a baseline level of distrust. They still make mistakes 5.8% of the time, even when the AI observer fed them perfect data, whereas the AI driver made zero errors under those exact same conditions. Interestingly, we observed that these phenomena became increasingly pronounced as the reinforcement learning agent underwent further training.
Now I will go over some things we learned and why this matters for the future. The simulation reflects our hypothesis by placing players in a direct conflict between a guaranteed visible reward and a less certain long-term reward supported by AI. To represent limited AI communication, the system could only provide one-word hints and classifications. Players therefore had to decide whether the AI's recommendation was reliable enough to justify sacrificing an immediate reward. We found that AI accuracy, limited communication, and driver visibility all influence trust. However, when players lacked confidence in the AI, they were less willing to sacrifice short-term rewards and most focused on what they could immediately see. Overall, we learned that people need enough evidence before following AI recommendations, and limited communication makes trust harder to establish, especially when the AI cannot clearly explain its reasoning. Some things we could have done differently would be increasing the value of the AI recommendation by adding potential points the user could earn based on the model predictions. Additionally, we noticed that users often resorted to squishing everything, and the skip button became redundant. So to fix this, we could add a penalty for killing healthy people. To conclude, one of the main goals of the simulation was to explore how we might repair the existing distrust between humans and flawed AI systems. Improving a model's mathematical accuracy is clearly important, but it is not enough. An AI system must also present its information in a way that feels convincing and trustworthy to the person using it. Even an accurate recommendation may be ignored when the user does not understand where it has come from or has not had enough experience with the system itself. This is especially important for human AI integration in high-stakes fields. AI could help classify immediate changes in the situation, while human responders remain focused on larger goals and the overall mission. Our simulation can serve as a simplified training ground where people become more familiar with the strengths, weaknesses, and limitations of AI systems. Looking towards the future, building trust will require several improvements. We need to provide users with training so that they understand the AI's abilities, but most importantly, we need to bridge the gap between an AI's judgment and a human's willingness to trust that judgment. This applies directly to first responders. Emergency situations often involve limited visibility and rapidly changing environments, a condition sometimes described as the fog of war. In these situations, an AI observer may have access to information that an individual responder cannot see, giving a better understanding of the overall situation. However, that advantage is only useful when responders trust the system enough to act on its guidance. AI should support and assist human decision-making rather than creating additional uncertainty. Ultimately, effective human-AI integration requires both accurate technology and human trust. By designing AI that is dependable, we can save more lives and build a safer future. Thank you for listening.
Hey guys, we're Team Alien by Amin, Aryan, Karunya, Harish, and Max. So our game explores how giving people an ability to undo bad actions will change human and RL behavior in environments of different complexity. So first we'll go over the base premise of our game, our research questions, and then the behaviors we thought we found.
Here's the game we started with. You're driving an ambulance through a zombie apocalypse, and every rescue is a gamble. You've got 720 minutes and 10 slots in your ambulance, and for every humanoid you come across, you've got 4 choices. Save them, skip them, squish them, or scram back to the hospital. That's the entire game we were given. No hidden risk, no way to undo decision, and no AI involved at all. It was our job to take this simple simulator and turn it into something that could actually study how people trust an AI that they can't fully verify. So here's what we actually added on top of that. First, carrier risk. This is a brand new hidden state that we built into the game. Some people who look completely healthy are secretly carrier of the zombie disease, and there's no visual way to actually tell. All you get is a number between 0 and 1, randomly generated, warning you about how risky that person might be. Second, we added the eject feature, the power to undo or rescue mid-run, actually pulling someone back off the ambulance after you've already saved them. And third, we made injured survivors take up 2 ambulance slots instead of 1, so capacity is always a real live constraint that you're fighting against. We also created a deluxe mode to test out how the RL model would work with more complicated scenarios. In the deluxe mode, we added a morale system. Every time you eject someone, your crew's morale takes a hit, and low morale actually slows down every future action that you take. 75% morale means 1.2x the time, 50% morale means 1.4x the time, and 25% morale means 1.8x the time, while 0 morale ends the game completely. And we also added blood tests. You get 4 per shift, and they're completely accurate, telling you if someone is really a carrier or not, but running one costs you 20 minutes. So now verification isn't free. It's a resource you have to decide whether it's actually worth spending on.
All right, so to reiterate, the core idea is how would human and AI decision making change with and without access to an undo button, the eject button. So surrounding eject, we had 2 main research questions. The first is on time. Will players choose to save faster with the option to eject? So more simply, will they become more impulsive if there's an easy way out? And the second is on risk. With eject available, would people take more risks and admit more people into the ambulance? This also ties into the carrier mechanism. So would people emit more because they feel protected? On the operator side of the person manning the ambulance, this answers the question of whether eject increases their objective save value, the amount of people they save and the amount of people they accidentally kill. And on the policymaker side, say you were in this post-apocalyptic world managing ambulances, you could answer whether eject should be implemented into future ambulances. Collecting human data. So for collecting human data on whether eject has an impact, we use a counterbalance within subject's design in which every participant played 6 games. And what counterbalance means is that 3 of the games are with eject on and 3 of them are off, and half of the participants will play their first game with eject on and half off and alternate. We also give them a practice round so they can learn the mechanics of the game before data collection starts. To log, we have a lot of broader metrics like how many humans they see, the time of their game, how many people they save. But on a finer level, we have metrics such as how much time they spend per move, which helps us answer research question 1 on time, and metrics such as carrier score, which allows us to measure the risk involved for research question 2.
All right, with all that wonderful data that Max just described, let's go ahead and analyze it in the frame of human testing. So let's start with the first research question on time. Take a look at the image on our slideshow. Each dot in this image represents a singular save decision of a humanoid made by a player. The time taken to make that decision is the x-axis, ranging from 0 to 40,000 milliseconds. And the top red clump of dots correspond to all of the decisions with the eject feature on. The bottom clump of dots represents to all of the decisions made with the eject feature off, Y buffers, just for the sake of visualization. As we can see, the clusters look the same, and the stats back that up. There is no significant difference in time for human save decisions when eject is on versus off. So we cannot conclude that the eject feature affects decision-making time. Moving on to the second research question, a carrier threshold we define per player to be the largest carrier score that a player would still, on average, take the humanoid in at. So for example, if a player has a carrier threshold of 0.25, if they see a humanoid with a carrier score of anything less than 0.25, then that player would save the human. Otherwise, they would skip or squish that humanoid. So each dot in the dot plot represents a single player's carrier threshold taken over many episodes. Again, red corresponds to the eject feature being on, and blue corresponds to the eject feature being off. On the image on the left, the data doesn't look very different in terms of the red and the blue data, but on the right, we see a clearer picture. Connecting the two dots for each player, we see that all of the slopes, except for maybe one or two, are positive. And this means that threshold score generally increases when eject turns from off to on. So we've statistically proven that people take more risky passengers when the eject feature is on compared to when it's off. The final bit of analysis that we did was ambulance capacity at Scram. So the x-axis is the number of ambulance slots that are used at Scram. The left side is when eject is off, and the right side is when eject is on. And as we can see with eject on, it's much more likely for a full ambulance to be scrammed than with eject off, because the 10 bar is much higher relative to the other values. This is because with the eject feature, the player has much more control over the ambulance size, because not only can they let people in and increase capacity, or increase the capacity used, they can also decrease the capacity used by ejecting.
Now let's talk about how we trained an AI to play our game. In reinforcement learning, an AI agent repeatedly plays the game by taking actions on an environment. After every action, the environment or the game returns a reward based on a function that we can engineer. And based on how good or bad the action is, the reward function is supposed to give it a score. At first, the agent plays almost randomly, but after thousands of games, it learns which actions consistently lead to higher rewards. So it gradually improves its strategy in order to maximize for the incentives that you provide it in the reward function. This means that the reward function critically defines what success looks like. We designed two reward functions, one that's supposed to be aggressive and another that's supposed to be conservative. The aggressive one is supposed to be a riskier one that takes on higher value carriers, but hedges that reward by ejecting people, while the conservative one is supposed to not take on higher risk and be more conservative in its measurements. As you can see here, we use a -1 to discourage taking on carriers, corpses, and zombies, while we only did a 0.5 discouragement for the aggressive model. But however, when we actually looked at the results, the conservative agent actually ejected twice as many patients as the aggressive agent, the opposite of what we intended it to be. Why? Because the agent wasn't trying to follow our intended strategy. It was trying to maximize the reward we gave it. Even though this reward is indicative of the property, indicative of the strategy that we wanted it to play, that's not what it learned. This is a great example of emergent behavior in reinforcement learning and broader AI training, where you are giving it a reward function to produce strategies that humans anticipated, but the AI learns a unique, a shortcut or some other strategies that are not the correct way to actually approach the situation. And it's very hard to identify these problems, and this leads to a class of problems known as misalignment in AI research.
All right, so let's move on to our base RL data analysis. So we sorted every game for both RL agents into the playstyles they had and mapped this onto the 2x2 figure shown in the slide. The left to right x-axis is whether we anticipate the behavior, and the bottom to top y-axis is whether it looks like a human strategy or AI native strategy. And three of these playstyles landed where we predicted with our hypotheses. On the right side, we see that the agents squish zombies and prioritize the injured, which are both human-like strategies. And then there's also the board then eject play up in the AI native side. The dot on the left is the behavior we didn't anticipate, which was a failure mode where a carrier sneaks onto the ambulance and wipes the entire load of passengers during the scram. Okay, so now moving on to the deluxe RL agent, where the deluxe RL can use a blood test, which actually lets the agent see if the carrier is truly a carrier. Our predictions clearly hold up. So the agent is following consistent thresholds for a specific action on the carrier number. So the left box plot is the proof for this. Each box is the carrier percentage it acted on for that decision, and there's sort of a ladder going from straight left to right, where it's saving when the carrier number is low, around an average of 25%, spending a blood test around the middle at an average carrier score of 47%, skipping above that, and then it'll squish anything that has a high carrier score, like around 76% average. And so we did all this analysis, and we want you guys to remember two key things. In summary, we saw how humans reacted to a rule change in the game, and we also saw how the different RL agents reacted. When eject was on, humans were not more or less impulsive, but it did fill up the ambulance by admitting more passengers. Meanwhile, the RL didn't change in reaction time, but we saw they barely ejected. So at the end, we learned something about ourselves.
We like to do riskier actions, but only if we can undo it. Thank you.
We're Team Immortal. Automation bias is a common issue well documented in fields like aviation, medicine, and security, including biometric identification, where operators often accept the system's top-ranked match without sufficient scrutiny. In July 2025, a facial recognition system misidentified Angela Lips, a 50-year-old Tennessee grandmother, as a suspect in a bank fraud case in Fargo, North Dakota. Fargo's police chief later acknowledged that the department had over-relied on the technology and that detectives had wrongly assumed the photo had already passed through certified facial recognition analysis. The problem becomes even more serious when the input is deliberately manipulated. Researchers have shown that adversarial perturbations to real images and faces can reliably fool classifiers and face recognition systems under real-world conditions, increasing the likelihood that both the AI and the human relying on it will reach the wrong conclusion.
We explored this issue with a game framework. Our main research question is, as the adversarial generator mouse budget increases, how does human classification accuracy and confidence change, and does AI assistance reduce the decline of performance? The mouse budget controls how much the red team AI is allowed to alter the image of an overgrown. A higher budget allows it to create a stronger and more convincing disguise. So what we compared were 4 difficulty tiers, where tier 1 is 0 edits, tier 2 is 2 edits, tier 3 is 8 edits, and tier 4 is 10 edits. We also compare participants who classify the images alone with participants who receive help from the AI assistant. For each decision, we measure whether the participant was correct, how confident they were, and how long they took to respond. We predict that higher mouse budgets will make the images more difficult to classify, causing accuracy to decrease and response time to increase. We also want to determine whether AI assistant reduces this decline or whether incorrect AI recommendations sometimes make human performance worse. So in our game, cosmic radiation has caused some people's cells to regenerate uncontrollably, turning them into creatures called overgrowns. The overgrowns are trying to enter a space station to spread the infection, and to avoid detection, they can alter their skin color and appearance to disguise themselves as healthy humans. The player takes on the role of a checkpoint officer. For each person who approaches the station, the player must examine their image and decide whether to admit them as a healthy human or reject them as an overgrown.
So what our game is the players in a first-person 3D world where they walk up to a checkpoint terminal to begin screening, and they have 45 seconds per image, as well as 3 zoom levels and a permit and reject button. So again, their goal is to let in any living human and reject any overgrowns, including the ones that are disguised to look human. And there's 30 images per session, as well as 2 modes. The first one being a human-only mode, which is just a human playing by themselves, as well as an AI assist mode where the player has an AI assistant which has a read on each of the subjects as well as confidence on the subject. And in the game, there are 4 difficulty tiers. The first tier being the control, which is just a human with 0 edits. The second tier has 2 edits from the adversarial AI. The third tier has 8 edits, and the last tier has 10 edits. So as the tiers increase, the adversarial AI has more edits and is allowed to change the zombie to look more like a human, which increases the difficulty. So how we built it, we used a convolutional neural network classifier, which is basically a image recognition model, and this acts as an AI assistant to advise the player. We also use a deep Q network reinforcement learning agent, which is basically a model that learns through trial and error, which acts as the attacker. So this agent could change the image through 2 ways. The first one being recoloring, which actually shifts the green pixels on the zombies to match a human skin tone, which fools the humans. And it could also tilt and slightly rotate the image a few degrees, which helps fool the classifier and degrade its confidence. So for example, if the agent rotated the images 0.5 degrees, that would count as 1 edit out of the 10 total edits at the highest tier. And the reward for the agent kind of acts as a tent, which peaks at the classifier decision boundary, meaning that would be 45% confident that it is a human and 55% confident that it is a zombie. So we try to create a 50-50 situation where the human at the highest tier either has to trust themselves or trust an ambiguous AI agent. And the AI confidence goes from around 96 to 80 to 69% across the 3 difficulty tiers. We also had a 490 image pool and narrowed it down to around 180 images with 30 images per session, as well as a 50-50 split between human and zombies, so 15 human images and 15 zombie images. And now we're going to get into our results.
So before we get to accuracy, let's look at how long people actually took to decide. So the gold line is the AI group, and they slow down as it gets harder. taking around 6 seconds on the hardest difficulty because they're actually weighing the AI's input. But the red line, that's people screening alone. And that actually speeds up down to 2.5 seconds. They're not getting more confident. They're actually giving up on looking and just starting to guess. Keep that in mind because it explains a lot about what you're going to see next. So this is accuracy across the same 4 tiers. For humans without AI, it falls off a cliff, down to 11% by the hardest tier. It's slightly better than random. With AI, it holds up a lot better, staying around 38%. And this lines up exactly with what we just saw. The alone group wasn't slowing down and being careful as it got harder. They were speeding up and guessing. So this graph is the direct consequence of the last one. Now this graph just isolates the difference between those two conditions, AI assisted minus human alone at each tier. So green means the AI helped, red means it hurt, and it's almost green everywhere, especially a 30-point jump at tier 3, which is exactly where people alone were falling apart and guessing the most. Tier 2 is basically flat since nobody needed help there yet. So the AI assist isn't equally helping everywhere, but it's overall beneficial. And this last one here is the survey data. So this is self-reported trust in the AI before playing versus after. So each line is one participant, and green means their trust went up, and red means it dropped. Gray means no change. So on average, trust actually went up slightly after playing, even though we know from earlier graphs that the AI was wrong a lot, especially at tier 4. So people ended up trusting it more than its actual performance probably deserved.
Okay, so this graph is specific to real humans who were injured in the scenario. We split it 3 ways: not injured with correct AI reading, injured with correct AI reading, and injured where the AI wrongly classified them as dead. So on average, AI assisted improved performance, but a problem became apparent when the AI was confidently wrong. Players' suspicion made them track the CNN's recommendation more closely than the image itself. They permitted most subjects the CNN correctly judge as human, regardless if it was confident or not. However, when the CNN was confidently wrong, misclassifying an injured human as a corpse, the permit rate fell to just 35%, which is lower than if players had received no AI assistance at all. The dashed line is the unassisted baseline. So here, the AI was actually making things worse.
Reflection part. So coming back to the reaction times chart on the left, the reaction times tell us that the players with AI assist take more time signaling that they might be actually processing what the AI tells them, and also their intuition about the human are presented. The pre-survey also signals that participants generally trusted in AI when presented with questions such as, I regularly use AI tools, I'm comfortable making decisions with the help of AI, etc. On a scale of 7, received average ratings of approximately 6 out of 7, suggesting that most participants were already accustomed to using AI and felt confident relying on it to support decision making in the game as well. The post-survey ratings too prove the same point. But it is interesting to note that trust did not mean blind obedience. When participants were faced with the question, there were times I thought the AI assessment was wrong. The average rating was 6 out of 7 on a scale of 7. It suggests that participants did not blindly accept the AI's recommendations. Even though they generally trusted and regularly used AI, they still questioned its judgments during the task. This indicates critical engagement rather than unquestioning reliance. To sum it up, AI assistance improved decision accuracy, particularly under high manipulation levels where human performance declined sharply. Participants did not blindly follow the AI. Although they generally trusted and regularly used AI, they still questioned its recommendations and exercised independent judgment. Trust remained high after the experiment, despite the AI making mistakes, suggesting people may continue to rely on AI even when its performance is imperfect. AI errors can have serious consequences. When the AI incorrectly identified as injured human as a corpse, participants were significantly less likely to issue a permit than without AI assistance. Overall, AI can meaningfully enhance human decision making in complex scenarios, but its recommendations should support, not replace human judgment. Thank you.
Hello, we are Team Upload, and this is our 2026 Serious Games with AI final project.
So within real-life decision-making systems, like in eligibility or risk assessment, information regarding a person is often reduced to a score, category, or a short description. So the concern is that representation may influence a decision even when the underlying value is similar. So for example, a rescue value of 84 out of 100 might summarize certain information accurately, but it cannot fully represent the individual. We wanted to explore whether presenting the same underlying worth in different ways would affect players' moral decisions. Thus, this led us to test several ways of presenting rescue value. So essentially, players received comparable rescue information in one of three formats. So a numerical score, a text rating, or that same rating but with irrelevant personal details. This allowed us to test whether presentation alone affected rescue decisions. Furthermore, we also varied how rescue qualification rules were worded to see whether players followed the intended criteria or were actually persuaded that an unqualified person matched them. So in other words, some characters may morph or glaze their description to convince you of their worth. We tested both questions through a game in which every rescue decision carried a measurable cost. In the last 100, players begin with 100 supplies and decide whether to rescue or pass each civilian. So rescuing costs 15 supplies, while passing costs 5, meaning players cannot make a decision without consequences. So this forces them to balance a person's rescue value against limited resources, giving us observable decisions. Now we'll show what that decision process looks like during the game.
Here is a quick demo video of our game. It is a bit sped up so you can see the full flow. So here we see a civilian profile. The player has to decide whether to commit to the rescue or pass by. In the first 3 rounds, players are shown either quantitative or qualitative information about the characters. Now the player writes a rule itself, defining who qualifies. They also had to explain their reasoning, which is really the point here. We're not just capturing what rule they chose, but also why. That rule is then tested against a set of real cases, and the system scores how consistent it is. And then in the last part, the player applies a rule that another participant wrote, so that we can see how well someone else's reasoning transfers to them. So over here, the player is trying to figure out how well they can apply the rule, and these are the results. The game tested 2 ways information shapes decisions. Rounds 1 to 3 were in an evidence format, and rounds 4 through 6 were related to rule interpretation. Round 1 is quantitative, with hard numbers shown as a rescue value. Round 2 is qualitative, describing the rescue value with phrases like low through high. Round 3 captures value in qualitative form as well, alongside with some intentionally non-relevant data, like a character's favorite shape. We wanted to see if the user's decision changes if extra information is given about the characters to sort of humanize them.
Through to rounds 4 through 6. The premise of these rounds was to simulate a natural phenomenon with rules. For example, if rules aren't created by the people that are enforcing them, there's potential for dishonesty for those who follow them, known as information asymmetry. We wanted to see if individuals could identify exploiters or liars better when they created their own rules and therefore understand the intent. So that was round 4. In round 5, these people inherit a rule. And in round 6, they inherit a rule with the numerical value, which may lead them to rush through and prioritize quantitative over qualitative insights.
So here's how some of us structured our research. Firstly, we would have participants play our game under a randomized seed, meaning the characters, values, and orders are randomized. This ensures that those variables don't influence human decisions. Afterwards, we tested 9 total LLM models and had them run through the same exact seeds so that we could compare specific decisions. Here were some of our results. For our rounds 1 to 3, we found that quantitative presentation had the lowest save rate of 53.2%, while the qualitative presentation had an average save rate of 60%. The addition of irrelevant details actually decreased the average save rate. Here are some additional statistics. The graph on the top shows average save rate across absolute value levels on rounds 1 to 3. The rescue rate depended more on the absolute value, and all 3 rounds show similar graph structures. We also measured the average time spent per decision across all 3 rounds. On the bottom graph, Presenting the value numerically resulted in the lowest decision time of 2.92 seconds, while qualitative is highest at 3.94. An interesting note is that when presented with the humanizing irrelevant details, average participant decision time decreased. This is interesting, as the total information provided to users is highest on this round. There are two possible explanations for this. The participant may not have been reading the details properly, or they may have gotten more familiar with the game, therefore being able to make faster decisions. Here were our LLM results. The top graph shows average total points for rounds 1 to 3, while the bottom graph shows resource allocation. Overall, Gemini's 3.6 Flash performed the best, having the highest total points and resource efficiency, followed by the flagship OpenAI models, then legacy and local LLMs. Comparing this LLM data to humans, human participants were able to outperform all LLM models except for Gemini's 3.6 Flash in both total saved character value and resource allocation. This shows that currently, humans perform at a rate similar to the top flagship models and do significantly better than legacy or local ones in high-pressure ethical decisions. In conclusion, while there were small observable differences in save rate across different presentation methods, these differences were not significant enough to be statistically relevant. Therefore, we cannot claim that presentation method significantly alters human decisions in these ethical environments.
Let's talk about rounds 4 through 6. On the top graph, we can see the save rate by round. And interestingly, every single model has its own trajectory, even those in the same family, such as OpenAI. O3, which is a reasoning model, climbed steadily, and O4 Mini and Terra both crashed in the middle round and then recovered. For Gemini, it's a different story. It drops and stays down, and humans are the only one with a straight decline on the whole way. On the bottom graph, we can see how many times a model or a human saves an exploited. O3, O4 Mini, Terra, and Gemini start almost flawlessly, under 1.5% of the time they save a lie. By the last round, that's 32 to 37%. Llama and Quen start at this 30% threshold and barely move, and the human line never actually gets better. Psychologically, this looks like moral licensing, which is a well-documented effect where behaving well earlier on makes one entitled to slip later. For example, someone who had a diet all week treats themselves on the weekends. And the reason why this doesn't happen with Llama or Quen is because they never had any slack to begin with. If we look at the top left graph, we can see what happens to exploiter save rates once rules get inherited. Every single model gets worse at catching liars once the rule isn't theirs anymore, which is a phenomenon matching psychological ownership, where people, and apparently models as well, enforce something far more carefully when they feel like it's genuinely theirs. When they inherit a rule, they follow the words without being responsible for what happens if it actually fails. On the bottom left, we can see the variation of models between games. Llama and Quen makes nearly identical choices every single game, but the other four swing by 50+% between runs, which is cognitive rigidity, which is the inability to adapt to new circumstances for these Llama and Quen models. Many may think that this consistency is more like a strength, but in the broader view, it just means repeating the same mistake every single time. Finally, this graph is our human versus AI save versus loop rate. On the left, we can see that humans save people less than half as often as AI, which inherently makes them more cautious in a way. But even through that, they're not as accurate. They get fooled 4 times as much as AI. At the end of the day, this shows automation bias for AI. It overtrusts a stated rule and always defers to it. But humans show something closer to reactance. When a rule is handed to them, some parts of them resist it. So the humans say no more often, but this doesn't necessarily correlate to actually checking more carefully. All in all, every one of these failures traces back to a real psychological pattern, because every model and humans stop following rules perfectly over time, but for different reasons. For example, O3 stops because he gets comfortable, humans stop because they resent being told what to do. But there are a bunch of different reasons, but there's always the same outcome, that nobody follows the same rules forever.
Thank you.
Hey everyone, we are from the Serious Games with AI course.
and we created a game called The Lost Souls of Jiangxi Island. I'm Aaron.
I'm Saf.
I'm Yana.
I'm Brielle.
I'm Zal. Okay, whenever someone points out that AI gets things wrong, the answer is usually that's fine. A person reviews it before it goes out. Hospitals do that, banks do that. This like human checking becomes like the safety net for AI errors. However, this only works if the person is actually looking and checking the entire time. And usually they're not sitting there with all the time in the world. They've got queue, they got things to do, a backlog of work. And going back and checking the AI's work takes longer than just going along with what it outputted. Thus, the whole safety net depends on people checking. And honestly, nobody knows when they stop bothering. We figured the only way to find out was to watch someone do it, so we built a game.
To tackle this problem, we decided to build a game designed around addressing the research question: how does time pressure affect behavioral reliance on an imperfect AI assistant?
The main intention of our game is to create a sense of pressure for the player while having them command exorcists by sending them to locations that contain Jiangxi, which are zombies. The game setting is on a fictional island off the Gulf of Tonkin in China, Jiangxi Island, hence the name of our game.
So the primary goal for the user is to allocate exorcists to zones on the island and free the inhabitants from the Jiangxi. So really how a round works is the user gets a set number of exorcists and there's a set number of Jiangxi to clear in each zone. And you decide as the user how many exorcists go in each zone. There's also an oracle in the game, as you can see on the right-hand side images. And this is essentially the AI assistant, and it gives you an estimate of how many Jiangxi are in each zone. But the caveat here is that in each session, the Oracle makes mistakes. The Oracle's errors can happen early, late, or be distributed evenly across the waves, and the pattern is completely randomized, which means the player never knows which. So this essentially gives the user two options. They can either trust the Oracle or don't trust the Oracle and use the cameras, which have a 100% chance of being correct, but it'll cost more time for the user. In the bottom right image, you can also see an example of what the surveillance camera looks like, and the amount of time to react decreases as the waves increase.
We rapidly prototyped a game over the course of 2 weeks, making all the models, assets, logic, and game loop by ourselves. We made our game in mainly Unity and C#, a workflow we were new to. The architecture consisted of Python localized server, relaying information to and from Unity for the AI logic, C# scripts controlling the models, UI, wave managers, and the main components to create a functional game loop for the backend logic. We decided to cut out our ideas to have multiple things aside from Exorcist for the players to allocate, as they would make our scope unachievable over a tight time period of 2 weeks.
For our hypotheses, our alternative hypothesis was that increasing time pressure on players leads to an increase in their dependence on the imperfect AI assistant. Our null hypothesis was that changing the level of time pressure on players will not change their dependence on the imperfect AI assistant.
Okay, so quick context first. We ran this with 33 participants, 30 in early, 10 in even, and 10 in late, and each person only played one condition, one full run through all 10 waves. Here's how we read what's coming. The table on the top shows the seconds allowed dropping every wave, 25 down to 12, so that's the pressure ramping up. The heat maps on the left shows where the Oracle estimate was off per zone, as you can see on the y-axis, and per wave is along the x-axis. The blue means it undercounted and the red means it overcounted, and they split out by condition. The line on the right is the cost of that. Mean zones on the lost on the y-axis added up by wave along the x-axis one line per condition. So quick summary, pressure ramps up every wave, errors were scripted into different waves depending on the condition, and the early condition already caused more zones even before we get into reliance.
So just building off what Yana said, as you can see in the left-hand side graph, this graph really shows the relationship between how waves increase and the verification rate. Just a quick clarification before we talk about this more. The verification rate is essentially how often players check the camera instead of just blindly trusting the oracle. So the overall pattern we can see here across all the early, late, and even waves is all conditions, verification rate peaks at around waves 3 to 4, and then it falls sharply down. And there's a really important consideration here because as you can see in the top diagram, as the waves increase, the seconds decrease, which means that pressure increases as well. So we can make the generalization here that as pressure increases, the verification rate goes down, which basically means humans don't use as much cognitive thinking and they blindly trust the AI. And it's also important to consider that in the late graph that we see here, the orange line, as compared to all the other conditions, there was a steeper and earlier collapse. And a plausible reason for this is because the oracle was correct early and players must have developed some type of trust for it. And this is why there was a more sharp decline.
Yeah, and the decision speed grab, it's up, seconds remain at commit is the y-axis there, waves number, the x-axis. So you can see it in a late condition, the orange line, people commit fast in the first couple of waves. That's because they haven't hit a bad call yet, so they trust it more by default. So these two charts pulls everyone together, no matter the condition. On the left, each dot is one wave. The y-axis is how often people trusted the oracle, specifically when it was wrong. The x-axis is second allowed to decide. On the right, same setup, but the y-axis is overall reliance instead. Often people just went with the oracle calls, periods, still plotted against seconds allowed on the x-axis. So on either chat, moving right means more time pressure. Reliance clubs clearly as the pressure goes up, the error equal negatively or 0.48 on the right, and misplaced trust moved in the same direction, just weaker and noisier, error equals negatively 0.23. So people lean on the oracle more under pressure. Next, here's what checking it cost them.
Due to increasing time pressure, trusting the oracle often ended up being the best choice of action for a player. Looking at the graph below, we can see that those who tried to verify the zombie count often ran out of time, and this resulted in them being unable to allocate exorcists to zones within the wave limit. However, in trials where the oracle lied, we can see that the difference in zone held rate between not verified and verified decreased, shown in the bottom right.
We learned a few lessons from challenges during our development process. First, every WebGL build took 40 minutes, so anytime something broke, that was 40 extra minutes before we concretely knew whether the fix worked, causing us to stop testing as often as we should. Through this, we learned that it is essential to allocate plenty of time to troubleshooting the deliverable, even if there appears to be no bugs within the code. Second, we should have allocated more people to work on Unity, since that became one of our tightest bottlenecks during development. Finally, we spent way too long making the game fun. Balancing waves, tuning the timer, argue about numbers. All of this felt like progress, but none of it really contributed significantly towards the study. And eventually we had to stop and ask what we were actually measuring. As a result, we decided to cut a lot of our polish and features for scope. If we did this again, we would build the logging first and the game around it, as that was a crucial issue that resurfaced within a lot of bugs and a lot of times.
So pulling it together, more time pressure means less checking on AI and more trust in Oracle. You saw that in the reliance number and again in decision speed. And it's not just early buy-in either. Even after a player watch the AI mess up under pressure, they keep trusting it and stop correcting course. Part of that tracks though. Checking costs time you don't have, and under pressure, checking can backfire. So leaning on the AI is arguably the smarter move once the time gets tight enough. One flag though, time pressure and game difficulty move together in our design, so we can't fully separate one from the other. Stepping back, this project taught us as much about building something as it about the research question itself. Cutting the scope, fighting the building, staying focused on the question. The same pressure we study show up in how we build this too.
It's fine. Can you guys see it?
Looks good to me.
Okay.
So whenever you're ready.
All right. Hello, BWSI, and welcome to our presentation on the differences among 4 types of deep Q network models. We will talk about how to understand data through algorithms in our games design. My name is Belinda.
I'm Emily.
I'm Braden.
And I'm Ben.
Our project was motivated by limitations of the standard DQN. In more complex environment, standard DQN can be unstable. So here comes our research question. Which DQN models perform best in our game? We compare standard DQN with double DQN and dueling DQN, and also double dueling DQN under the same game and the training environment. Our hypothesis was that double dueling DQN will perform the best because it combines the advantages of both double and dueling DQNs. So, double dueling DQN will be more stable and better when performing.
So in order to test this hypothesis, we decided to create an environment in Unity. So this game is our environment, and the player will play as a ambulance driver in a 2.5D world. Throughout the road, there will be randomly spawning entities, humans, zombies, and cars. The goal of the game is to gather as many points as possible. The player will do this by running over zombies, avoiding humans, and most of all, avoiding cars, because that will reset the run.
So let's start with the basics. What is reinforcement learning? Reinforcement learning is an algorithm that learns to make the best decisions by taking different actions in an environment through rewards or penalties. Through reinforcement learning, an algorithm, it functions through a cycle of states, actions, and rewards. As the agent begins, it describes the state in its current environment while selecting an action based on its policy, mapping the other states and actions. The environment then provides a reward per action, allowing the reinforcement learning to choose a next state. An equation is then utilized to define a state's value as the immediate reward plus a discounted estimate of the best value from the next state, calling on itself. Over episodes, this process repeats, allowing value estimates and policy to improve, leading to reliable decisions that maximize total rewards. Thus, we use a type of reinforcement learning algorithm called Q-learning to create our game.
So our game is developed in the Unity game engine, and our environment gets an observation of the current environment state and passes it to the agent. The agent then uses its internal model, which in this case is refined by DQN, to predict the best possible action and take that action. The environment then updates after the action and sends a transition between the previous state and the next state, along with the reward to the agent. And it uses DQN to update the internal model and improve the accuracy of predicting the best possible action. The different reinforcement learning algorithms we use, specifically variants of DQN, are base DQN, which is just a neural network that predicts Q values or quality values for every single possible action. Double DQN, which uses 2 neural networks to reduce overestimation bias that is often present in the base DQN. Dueling DQN, which uses a single neural network, but splits it internally into a state, value, and advantage stream. And this allows it to better predict the differences between good states and good actions. and double dueling DQN, which combines both double and dueling DQN to create an overall model. This is just a basic architectural overview of the different DQN models. So basic DQN has one network, predicts the future rewards for every action, and then takes the best action. This often leads to overestimation bias, where it thinks it's doing better than it is. Double DQN solves this by splitting it into two different neural networks, an online network and a target network, where the online network is the one actually taking the action, and the target network is evaluating the result of that action. Finally, dueling DQN uses a single network, but splits it into two streams, an advantage stream and a value stream. The advantage stream is how good a current state is, and the value stream is how good each action is in that state. And then it combines those values and uses that to take the action. Finally, double dueling DQN is a combination of both double DQN and dueling DQN.
So this is a video of our agent playing the game. Now, as you can see, there's raycast lines so that the agent can see the different objects in its environment. Also, the agent tends to stick to the walls because that's a safer way to play and it doesn't have to risk hitting the cars in the middle. This is a graph of our 4 different DQN models. So this black line represents episode 215. So the first 215 episodes were spent training the AI how to drive, and there were no penalties or rewards for hitting zombies or humans. After episode 215, we added penalties and rewards for hitting zombies and humans, but it didn't make a noticeable difference on the agent's driving. Now, the very bottom line is the standard DQN, and as you can see, it's relatively flat, which means that it didn't learn. And although it's hard to say exactly why this is, it's likely because it couldn't find an optimal policy to use. The next one up is the double DQN, that's the gray line, and the shape of the double DQN is very similar to the double dueling DQN. Again, it's hard to say exactly why this is, but it likely has to do with the fact that it's a double DQN architecture. Also, the orange line is the dueling DQN, which performed better on average than the double DQN, which was something that we had originally predicted.
Now, I will give a few conclusions for our main findings from the data. So first, the standard DQN performed the worst overall, showing less stable performance throughout the training. Double dueling DQN has the longest episode duration, so it was able to survive the longest time in our game. And one thing we found interesting is the agent learned a wall hugging strategy, which Emily mentioned before. And that's because under our reward function, staying close to the wall acted as an emergency strategy because it reduced the chance of colliding with obstacles, for example, like cars, and that will restart the game. So we don't want that to happen. As a result, the agent just prioritized safety over just aggressively like hitting the zombies to get coins. This wasn't the behavior we originally expected, but it is really something interesting to see.
Through these results, it implies that we must make some changes due to the diverting actions that our Q learning has taken. Towards the AI algorithm, we would redesign the reward function to implement a loss for hugging walls, forcing our Q learning algorithm to actually go towards its intended goal of hitting zombies. The observation space for the Q learning would also be tweaked, reiterating the raycasting beams. In Unity, the environment is currently basic, only having 3 different obstacles. To increase diversity, more obstacles would be added. Additionally, the driving environment would also be changed to allow more randomness through possible items such as stop signs or objects moving side to side. To add, the map would also be extended for more exploration through different roads that extend from side to side, while allowing intersections. Overall, our base game is sufficient for testing, but of course, it can always be better.
Thank you so much.
All right. Hi, my name's Advik. We're Team Viral. I'm here with Annabelle, Aiden, Hannah, and Yuli, and we're going to be presenting our final project.
We had 2 main research questions for our game.
Do human players adhere to their decision-making framework under pressure? And do reinforcement learning agents adhere to the reward-coded framework any more reliably than humans do?
Knowing whether pressure affects the consistency of human moral reasoning differently than AI matters because it improves our understanding of when each can be trusted to make decisions. This is also becoming increasingly relevant as AI takes on more real-world decisions, and knowing when its judgment can slip can help us build in safeguards.
So to test our research question, we made a game with code, art, and sound effects, and attached a survey form to prompt players to answer a few questions before and after playing, evaluating how they would make decisions. And we also trained an AI agent to play the game and gather more data for comparison.
For human play testing, we wanted to analyze how people would make decisions in a pandemic situation and compare what a person says they did or would do versus what they actually did in game. With reinforcement learning, we wanted to compare the AI's decisions with the human data and observe how different reward functions change how the AI agent plays the game.
So we made our game in the Godot engine, and here we can see screenshots from the game. This includes the main menu and comic introduction, tutorial, upgrade tree, and two screens for results and analysis. So this is the UI of the main scene in the game. Each of the 25 squares, apart from the one in the middle, represents a neighborhood, and the zombie infection starts at the cell labeled origin, and cells adjacent to infected neighborhoods are at risk of spread. On the right-hand panel, players can choose a neighborhood to treat, kill, or just pass that turn, and they can also access their skill tree on the top right and view their stats and settings on the left.
All right, so here's a quick overview of the reinforcement learning. We used a DQN agent from the baseline code, and we built the environment and reward function ourselves and trained 4 agents under different ethical settings, as you can see in this table. Mode D is the only one that's different, as its reward function only scores the final survivor count and nothing else. And as for modes A, B, and C, they follow the same specific reward function structure, but with different kill costs, as you can see in the table. And to test that the AI is actually skilled and the game isn't luck-based, we compared a trained agent to an agent that does random actions. Here, win means 75% survived or more, and trained clearly beats random in every mode. Random still wins 40 to 50% though, since the AI doesn't pick which cell to act on, as it auto-targets whichever neighborhood scores worse. Next, we can see in this graph, modes A, B, C punish killing 1, 2, 3 times in that specific order. Mode A uses clear 6% of the time, which is basically killing. Mode B uses it 18% of the time, which doesn't really make sense as B punishes killing more than A. So it should theoretically kill less and not more, and I'll explain this a little bit more. Mode C drops to 0 kills and Mode D sits around 63%, and that was expected since Mode D has no penalty on killing at all. So again, more than 75% survive counts as a win here, and humans won about 22% of the time at this win threshold, and every AI mode wins significantly more, ranging from 80% to 90%, and Mode D is the lowest of the four since its reward isn't as specific, and Mode B is actually the highest here. The bottom chart shows the full spread of survival rates for a clearer look at each one. So now this is a more comparative graph. It compares the win rate of the human and the 4 different modes at every possible threshold, and not just one number, with markers at 50, 75, and 90%. You can see that the humans decline in a pretty linear line, and the AI modes are pretty much at like 100% win rate until around 70%, where there's a slight decline, and at around 75%, they start to separate clearly, where mode B is higher than the others, and by 90%, mode D actually ends up higher than the rest. Now, this is what the AI did compared to the humans. The humans used clear about 40% of the time, which was way more than modes A, B, and C, each at 6%, 18%, and 0%. This isn't necessarily humans being less ethical though, because we never scored killing as worse for the humans, and that penalty only existed on the AI side. So people use clear whenever it felt like the faster and safer decision under pressure. Mode D is the only one that killed more than humans did, since it has 0 restrictions on killing at all, like I said earlier. What we think is the reason for B's clear percentage being higher than A is Mode B gets penalized more for killing, So early on, it hesitates and relies on treat longer than mode A does. But that hesitation can lead to an outbreak to grow worse in some games, as treat actually doesn't prevent spread as much as clear does. And once it gets bad enough, killing becomes the only way left to contain it. So B can end up forced into more kills later on in the game, even though it wanted to kill less at first. However, we only train each mode one time on one seed, so we can't say for certain this is a real pattern versus something that will look different if we trained it again.
Next, we wanted to take a look specifically at the human data. So first, we compared the pregame survey responses with the postgame survey. So in the pregame survey, we asked players if they valued fairness or effectiveness more in a pandemic situation. But this ended up not having much correlation with whether players chose to cure zombies or kill them, implying that the act of clearing zombies probably didn't carry much moral weight in the game. And this echoes what we observed earlier when comparing human and AI decision making. The confusion matrix on the right also shows this. Correlation between survey response and gameplay is indicated by the diagonal, and contradictions are off of it. And as we can see, both halves basically each make up half of the total player count.
Okay, so for the next result, almost half of the players misidentified their strategy style, with 35% saying that they adapted their strategy to specific situations. But we found that they actually maintained a pretty consistent approach, which kind of implies that people often stick to an underlying consistency even when trying to adapt. Here are some other results that weren't as unexpected. Players mostly maintained their attitude toward rule flexibility and were good at generalizing their actions for cure versus clear. However, they did often misidentify whether they focused on preventing spread or reducing hotspots.
Lastly, this is just an overview indicating if players' actions followed how they believed they acted, with the portions in red indicating a contradiction between their actual gameplay and their responses in the post-game survey. So the prevalence of red in the bars indicates that a lot of times players misidentify how they're acting.
All right, so onto the actual game data. Here is a chart of the average values by ending. So we can see win, which in this case is greater than 50% of the population remaining at the end of the game, and then we have Pyrrhic win, which is less than 50% of the population alive at the end of the game. In this next graph, you can see that most Pyrrhic runs don't actually have any doses of their vaccine left, meaning they use all of them up in the beginning or at some other point in the game, while true wins do not fully utilize their vaccine doses. So this represents kind of a big deviation from typical norms, right? You usually want to exhaust all of your resources, but in this case, we see that the data implies the opposite. You don't want to exhaust all of your resources, especially not early on. In terms of action variety, we can see that in winning cases, there was a healthy mix of clear versus cure in the beginning of the game, with wait being kind of a redundant option. But the latter half of the game, clear usage saw a healthy increase in order to secure the win until the vaccine arrived. Another huge note on the right-hand side, you can see there's a graph showing that many of the skill upgrades that were typically associated with treatment upgrades on the micro or neighborhood scale were bought by people who got the Pyrrhic win outcomes, whereas macro buys like quarantine were significantly correlated with winning outcomes, as well as the surprising reinforced clear. So overall, upgrades that de-escalated the situation were preferred over ones that treated on the neighborhood scale from a pure utilitarian perspective, even reinforced clear. Now, another thing to note is the median money amount for Pyrrhic wins. You can see in the box plot for Pyrrhic wins on the left-hand side that the median money amount is very high, around 550 or 528,000, and 25% of the amount of Pyrrhic win data has money amounts between 510,000 and 600,000. It seems from this data that we can conclude some players attempted to either invest big in cures, but then stopped after unlocking all the upgrades that they needed, or they weren't aware of the other different upgrades within the upgrade tree. The latter assumption is confirmed by the activity log on the right-hand side. Not enough Pyrrhic win data points are plotted on the graph to the right, meaning that indeed not enough people invested in skill trees, even though they could have.
So now on to future work. This project highlighted several questions that we could explore with future research. So first is whether there are meaningful differences in reinforcement learning performance when agents are trained in a cloned Python environment versus directly within the graphical user interface. Another question we brought up was whether our DQN reinforcement learning algorithm was the most effective. And so we could investigate other algorithms and see if they're better suited or more effective for utilitarian decision making within a pandemic scenario. We'd also like to examine how different visual signals within serious games could influence the variability of player responses, and finally, how we could best simulate real-world pandemic scenarios within a virtual environment.
Thank you.
Hey everyone, thank you for watching us today. We're Team Psychic, and for the past 4 weeks, we've been researching on human and AI teaming. I'm Caleb.
I'm Livia.
I'm Brian.
I'm Ty.
And I'm Alex.
Today, we'll be walking you through our research question, the design process, the data we collected, and the results from this experiment.
For our research question, we're asking two things. Does a player's decision-making change as they become more on AI, and does the AI's confidence level actually matter? And second, does decision quality or override rate shift as pressure increases? In our game, players rescue survivors while escaping an incoming horde. We hypothesized that once players lose the ability to identify people themselves, they'd rely more on the AI's classification and confidence. But as the horde gets closer, we expected their willingness to rescue someone to drop in favor of just saving the ambulance.
So here we're introducing our game design. So our game design was inspired by combining two very different experiences, Subway Surfers and MIT's More Machine Game. So from Subway Surfers, we took the fast-paced and under-pressure running style, where the player has to keep moving quick and make quick decisions while being chased. And from the Moral Machine Game, we took the idea of making difficult ethical decisions regarding who should be saved. So here we have our game trailer. Credits to Livia.
So now let me walk through how our game plays. The mission is simple. Get your ambulance to camp before the horde catches up. Each turn a person appears and you decide their fate. Skip moves you forward slowly, Squish is fastest but costs you if it's a healthy or injured human, and Save loads them aboard but doesn't move you forward at all. One risk with Save is if you accidentally load a zombie, it kills everyone in the ambulance. The ambulance also has a seat limit. Once full, you can't save anyone else until reaching camp. Engineers give a distance bonus and medics can cure injured survivors. Players run 2 rounds with stats carrying over into a combined total. The core mechanic tying all of this together is the horde meter. No matter what choice you make, the horde always keeps advancing, so it tracks how close the horde is at all times, and it's what creates the pressure behind every single decision a player makes. To test our hypothesis, we added 3 main parts. The centerpiece is the horde meter itself, replacing the original timer, a progress bar tied directly to horde distance that drives the pressure behind every decision. We also added an AI suggestion feature that gives players a classification along with a confidence level and a possible split-screen decision format for how choices get presented. The horde meter is what lets us test that override rate question. The AI suggestion feature is what lets us actually measure reliance and whether the AI's confidence changes how much players trust it. Blur and grayscale are added in the second round. This ties into the other half of our hypothesis that as players lose their own ability to clearly classify people, they'll start relying more on the AI's classification and confidence instead.
Next, we're going to have an overview of the data collection. So what data is collected? We collect our data in events, and for each event, we log 3 things: the game state, the player's action, and the CNN's output, and it's all organized by round. So the game state has the person type, which could either be healthy, injured, zombie, or corpse. If the role is healthy, then the role can either be civilian, engineer, or medic. There could also be a certain number of people, so either 1 or 2. It also records the horde distance. It also, in the data collection, records the actions, which could either be skip, squish, or save. The CNN output predicts the person type and the confidence score, and that's logged in our data. We also log the different rounds, so then we could compare how players play when there isn't blur versus when there is blur. So even with a small number of variables, there are many possible combinations of things to graph. If we try and graph all of them to find any correlation, that creates real risk of p-hacking, especially with a small data set. To reduce this risk, we choose our visualizations and metrics before we collected the data, based on what we hypothesize would matter, rather than searching for patterns afterward. This doesn't eliminate the risk, the data set is still small, but it's a deliberate step to reduce it.
So here's our conclusion section where we're going to look at our trend results from our data, any future additions we'd like to make to the game based on our observations, and any ethical questions raised by the game. So here we have the blurred vision on the player's performance. So basically here, each pair of bars represents one player. So the blue bar shows that a player's percentage of savable people saved in round 1, while the red bar shows their percentage in round 2. The y-axis here shows the save rate, so basically a taller bar represents better decision quality. The final pair of bars shows the average across all players. So our main finding from this was that players tended to save fewer people in round 2 after their vision became blurred and they had to rely on the CNN classifier. We made it so that round 2 made it so that players were less capable of relying on their own vision, which could have pushed them towards using the AI more. However, as we can see from the results, their performance decreased without a clear increase in agreement with the CNN. This means that becoming less capable of making an independent decision did not automatically make players use the AI more effectively. So here we can see the horde distance influence on the player's decision making. So here, the x-axis shows us how far the player was from the horde, while the y-axis is showing us the percentage of correct decisions. Each point here represents the average performance at that distance. So for example, at a medium distance or about 20 feet away, we can see that players saved around 77% of savable people in round 1 and 56% in round 2. So for context, the horde moved 10 feet closer each turn, so players had to balance making careful decisions while staying alive. So our main idea here was that players performed much better when the zombie horde is further away. We believe this is because when players are under less duress of the incoming pressure from the zombie horde, they performed much better in terms of players they were able to save, and their chances of accidentally squishing someone who wasn't a zombie decreased. Overall, players performed much better when the horde is further away. From what we noticed, their preferred range appeared to be from medium to far range, so from about 20 feet to 30 feet, where they had much more time to consider the character, AI's recommendation, and compare with their own judgment. This directly ties back to our secondary research question because the decision quality clearly shifted as the horde closed in. This showing us that human AI decision making depends not only on the AI, but also the pressure of the environment.
Players also didn't rely on the CNN as we expected. We expected AI reliance to scale with confidence and to increase once the visual cue was removed. However, neither happened. On the top right, we can see a CNN confidence versus percent of player agreement graph. We can see no steady relationship between the CNN confidence and the player agreement, meaning CNN confidence wasn't much of a factor. Removing the visual cue didn't also really increase reliance. On the bottom right, we see percent of times players agreed with CNN by the round. Agreement actually decreased in round 2, shown by the red bar, instead of approaching 100% as we expected. Players relied more on their own judgment and intuition rather than the CNN, applying caution rather than defaulting to blind trust. Possible factors could be horde pressure influencing decisions, CNN classification/confidence was not visible enough for players to notice, or other things.
A common behavior was that players prioritized building a safe lead from the horde before rescuing additional survivors. Players were often willing to squish injured civilians if it helped them gain distance. Once they had established a comfortable lead, some even began skipping zombies instead of squishing them, allowing them to spend more time rescuing. Another interesting finding was that engineers were consistently prioritized over medics, suggesting that players valued the engineer's movement buff more than the medic's ability to rescue injured civilians. The most interesting observation we had was that players' personal experiences influenced their decisions. Since most of our data came from people in this course, everyone had built very different games. For example, one participant hesitated to kill zombies because in their game, zombies could be cured. Another participant mentioned that their game didn't include injured civilians or corpses, making them more willing to sacrifice injured people if it helped them escape the horde. These responses suggest that players brought habits from their own games into ours, influencing both their moral and strategic decisions.
In terms of ethical questions, our game addresses and reflects utilitarianism, where the goal is to save the most people. While rescuing the injured civilian would be an empathetic choice, saving the engineer often leads to better overall outcomes. Players must decide between helping one person now or maximizing the number of lives they can save overall. The CNN model and the Players Limited site further develop this question, as players must decide whether to trust an inaccurate system and risk picking up a zombie or leave another civilian or injured behind to die.
Going forward, we'd expand the scope with more rounds and harder horde chases, retune the CNN's accuracy, and make the medic's effect visible. Right now, it's mentioned in the rules, but the medics can only heal people at the end of each round. We would change it so that the medic's effect is more visible during the round itself. We also found a bug where getting caught by the horde doesn't actually kill your passengers in the score. Our CNN currently runs at around 70% accuracy, and the next step is swapping in a deliberately weaker version of the CNN and rerunning the playtest, comparing the override rate and outcome quality against our current model. The question is whether a worse AI makes players override it more because they notice, or whether override rate stays flat.
Thank you.
Thank you.
Thank you.
Ew.
Thank you.